This meeting is being recorded.
Okay.
Yes,
I
sir.
think now it is audible. Okay.
Yes, sir.
So we'll start immediately.
1 second, sir. I will make you co-host. A very warm good evening to one and all. Welcome to day 2 of our FDP. I hope you all had a great learning experience yesterday and are looking forward for today's sessions. According to today's schedule, we have our first session on mathematical foundations for quantum computing. This is an essential topic as it lays the groundwork for understanding the complex yet fascinating world of quantum technologies. It is my pleasure to invite distinguished speaker Professor JyothiRanjan Nayak sir for this session. He is a professor of mathematics at the Faculty of Science and Technology ICFAI Foundation for Higher Education. With his extensive expertise in teaching and research, he brings a wealth of knowledge and experience to this session. His teaching areas span a wide range of mathematical disciplines, including operations research, optimization techniques, linear algebra, number theory, and cryptography. On the research front, his interest lies in optimization theory, fuzzy sets, and optimal control theory. Professor Nayak sir holds a PhD from Utkal University, Bhubaneswar, along with an MPhil and MSc from Behrampur University. Throughout his illustrious career, he has guided many scholars to the successful completion of their PhDs, published numerous papers in reputed journals, and served as a reviewer for both national and international journals. We are fortunate to have him here today to provide us with a deeper understanding of mathematical principles underlying quantum computing. Thank you, sir, for accepting our invitation and having here.
Thank you, Dr. Silpa. So we'll start directly. Okay.
Yes, sir.
Okay. So I have no PPT. I'll be writing everything on my Wacom pad. Please cooperate. Share.
You have to share your screen, sir.
Okay.
ఉన్నప్పుడు చేసుకోవాలి ఏదో ఒకటని.
My screen is visible now?
Yes, sir.
Okay. So we have mathematical foundations. Students. Like this. Is this clear or it is hazy?
It is not clear, sir.
It is bit hazy, na?
Yes, sir.
Do it. Okay. Let's see. 1 pixel will not come. Is it okay? Not visible.
Yes, it is visible, sir.
But not so clear.
Yeah.
I don't know why it is breaking. I am doing on Paint actually.
Sir, in WebEx app only you have whiteboard options.
Check it. Check it.
After beside end meeting, you have 3 dots, na?
There. Whiteboards.
Yeah, if you click on that whiteboard option.
Okay. I think it is okay. isn't it? And this is the pen. Clear now?
Yes, sir. It's very clear.
Okay. That cursor will be plus or something else. Okay. Okay. I'll erase it. All right. We'll start directly. No issues. So, for quantum computing, we need this. We need complex numbers and linear algebra and probability is already there, but we will not discuss about probability in detail, but complex numbers and linear algebra is a must. Okay, so I'll be going thoroughly through everything. Okay, I think we all know complex numbers, but still for refreshment I'll write it like this. A complex number, because these will play important role in quantum computing actually, is an ordered pair xy, okay, presented as x plus I y. Both x and y are real numbers. I is equal to square root of -1. Why we are exercising all these? Because what happens in many real life situations, we cannot have always equations like this. X square is equal to 4 or x square is equal to 9. Okay. Full screenshot. How to get it? Full screenshot here. 100%. This is already 100%.
On about the
Layout.
participants, you can make your screen as a full screen. Then it will be visible.
Okay, I am not conversant with all these things very much, but I usually give like this. Okay.
Yes. Sir.
Okay. Have patience. I will explain everything. No issues. So whenever we come across a situation like this, x square plus 4 is equal to 0. To solve this, we put equal to -4. So how to get the root? This -4. So this creates this I -1. Okay. So one point is how to represent a complex number in the plane, in the complex plane. Okay. So we can treat it as a vector, two-dimensional vector. You see, suppose we have 1 plus 2i plus 2i. So this is the real axis, this is the imaginary axis, and we take 2 units here and then move 1 unit up. So this becomes our complex number. Okay. A plus IB or something, AB. Now this is the origin. Now you see that this arrow AB will be playing very vital role in quantum computing, particularly on the block sphere. Okay, we'll go step by step. So this is one way of representing a complex number. Another way is this angle theta and this length r. R is equal to a square plus b square, and theta is, in fact, tan theta is equal to b by a. Okay, so theta is equal to r tan b by a. Okay. So this is very important because usually we put a complex number like this as r e to the power I theta, r e to the power I theta. And usually all quantum states will be presented in this form. Okay, so let my complex number be z is equal to say a plus ib. Same thing can be written as r cos theta plus I sin theta. And we represent by Euler's formula as e to the power I theta. Okay. And magnitude is r. This theta is the angle through which we can rotate through the plane. Right. So we will be presenting, suppose this angle is pi by 4. Let theta be pi by 4. And we represent a number like this, 2 e to the power I pi by 4. Where we are then? On the plane. We are on a circle of radius 2. We are on a circle of radius 2. Okay. That circle. Okay. And we move angle pi by 4 here with an angle pi by 4. Okay. This. So we move like this on the boundary of the circle. This radius is 2. Okay. So once we change the angle, we move our position into different places on the circle. Okay. And in quantum computing, mostly we will be using this type of expressions as different states of the inputs. Different states of the inputs. Okay. So how to add complex numbers? We know it very well. I think everybody knows it. Adding complex numbers, then multiplying complex numbers, we know it very well. Okay, I'm not going to that. Only one point is, that is conjugate. That is very important. Conjugate of a complex number. If a plus ib is the complex number, a minus ib is the conjugate. Now a plus ib multiplied by a minus ib will be how much? A square plus b square. Okay, this is a real number. These are already known to everybody, but I am just refreshing because shortly I will be going to the qubits. Very shortly, after we discuss about something about matrices, I will go to qubits. Okay. Now we are going to entering into linear algebra, matrices and vectors. Okay. Vector means it is always a column vector actually. Say 1, 2, minus 1. Okay, so this is my V. If I say V transpose, how it will look like? It will be a row vector. 1, right? And it has got 3 rows and 1 column. So this is a 3 cross 1 matrix. This is 1 row and 3 columns. 1 cross 3. Okay. So why we need matrices? Okay, we solve linear equations, simultaneous linear equations. Actually, a matrix helps us in transformation. Okay. For example, suppose we have got a vector 2, minus 1. I multiply a scalar 2 to 2, minus 1. So it becomes 4, minus 2, doubled. That means if this vector is here, 2 units here and -1 here. It is like this. Now I multiply by 2, it is increasing by another unit here, doubled. Okay. Similarly, I have just multiplied a scalar. Now I will operate a matrix on it. It will change its position. Some change will be there definitely. So let me put this like 0, 1, 1, 0 on 2 minus 1. We know multiplication. This first row and then this column. So 0 into 2 plus 1 into -1. That is equal to -1. And then 1 into 2, second one, what is equal to this is the first element, and what is the second element? We'll get it. 1 into 2 plus 0 into this one. This is the matrix. So 2 by 2 matrix. This is 2 rows and 1 column, 2 by 1. So you get a 2 by 1 matrix. And in fact, this is a vector. And this is -1, 2. What has happened? 2 minus 1 has become -1, 2. That means this vector 2 units -1 has gone to -1 . This is -1, say 2. This 2 units height. Okay. This has flipped. This has flipped. Okay. So we will be using such situations all the time in quantum computing, flipping things, rotating things. In fact, our inputs, which are called qubits. Okay. Let us go exactly as per the prepared lecture. I'll tell you everything. Okay. So, now suppose we operate this matrix 1, 0, 0, 1 on some vector AB. We will get again AB. This is the identity matrix. This is the identity matrix. So suppose I take another matrix 2, 0, 1, 1 into AB. What shall I get? First element is 2A, 0 into B, 0. Second element is A plus B, A plus B. Okay, 2, 0. Is it okay? It's not okay. Please mark it and tell me. You can tell here. It is A plus B here. Below that. A plus B. So 2 by 2, 2 by 1, we get a 2 by 1. See here, when identity matrix was there, there was no change. But changing some value in the matrix, now it has changed its value completely. That means its shape, size, everything will change, right? And the direction will remain as per the direction eigenvectors of this particular matrix 2, 0, 1, 1. So while moving on, these things will take care of our inputs and they will be converted to qubits in such a manner that our domain where we are operating and we are trying to do some operation or programming on our given data, we can transform our input data into qubits, which will be fitting to quantum computing. Okay. In that, we need inverse matrices. A is given. What is A inverse? Square matrices with non-zero determinant only possess inverses, because A inverse will be the identity matrix. That means if we operate A on X and before that we put A inverse, X will not change its position. It will remain at the same place. Okay. So that means as if we are operating the identity matrix on it. But actually the data is in the form of AX. Okay. Now, here one matrix plays very important role, that is called unitary and Hermitian matrices. Let me write a matrix like this. Let A be a matrix whose elements are both real and complex. And in the entries, we have got like 2 plus 3, I say. This is 0, this is 5, and this is 3 minus 5. So a complex matrix. Now, what is A transpose? A transpose is 2 plus 3i, 0, I, 3 minus I. Now, what is A transpose bar? Complex conjugate of it. 2 minus 3i, I, 0, 3 plus I. Okay. Now, if you multiply A transpose bar and A, what shall we get? That is important. Okay. This type of matrices are Hermitian matrices. We'll check it. Okay. We'll check some small examples where we can do it. So Hermitian matrices play a very important role in our quantum computing. Okay. That means its inverse is the complex conjugate. Hermitian matrices have got their conjugate as the inverse complex conjugate. So we write them like this: A star, in fact this is your conjugate, its transpose is equal to also A transpose conjugate is equal to, we name it as A dagger. This is called dagger. This symbol is called dagger, right? And this is for Hermitian matrices whose inverse is the transpose conjugate transpose. Okay. So if its all rows are orthonormal means, see here, let H be a Hermitian matrix. Okay. That means its diagonal mainly 2, 3. Diagonal is real. If I write 1 plus I here, right, and 1 minus I here, it becomes Hermitian. Okay. H is like this, the Hermitian matrix. Sometimes what happens, we have matrices like one by root 2 like this. Let this matrix be U. We name it as U. I am taking 2 by 2 for understanding. 1 by root 2. 1 by root 2. 1 by root 2 I minus 1 by root 2 I. Okay. Now see what happens. 1 by root 2 square plus minus 1 by root 2 I square is how much? 1 by 2 plus I square is minus 1. So 1 by 2, 1 by root 2 minus 1 by root 2, 1 by root 2, this square and sorry, minus I square. What is the value? 1 by 2 and minus, this is 0. Okay. And again, if you take the other one, that is 0. Another thing is you take the dot products. 1 by root 2, sorry, 1 by root 2, this column, and minus 1 by root 2 I, its transpose. Okay, into means this is the row vector now. Okay. In fact, I am writing this column as a row vector and its transpose multiplied by 1 by root 2. 1 by root 2 is minus is here. So when you multiply, their dot product will be 0. That means they are orthogonal. They are orthogonal. Okay. So a matrix, complex matrix, whose rows and columns are orthogonal, that means perpendicular to each other, and the determinant of the matrix is 1 or minus 1, then it is called a unitary matrix. Unitary matrix. Unitary matrix. And we denote it as U, and U dagger will be identity matrix. We will be using this as a gate in quantum computing. Okay. So Hermitian matrices, unitary matrices, orthogonal matrices, orthonormal matrices, they matter a lot. Okay. I'll give you some concrete examples because I took it from my mind. Okay. Let A be equal to 4, the diagonal is 7 here, 4, 7, 1 minus 3i, 1 plus 3i. Because this lecture, are you recording? Shilpa madam? Hello? This lecture will be shared with everybody, you can take it. Okay. This is a Hermitian matrix. If you take the eigenvalues, the equation will be lambda square minus 11 lambda plus 8 is equal to 0. This lambdas will also play an important role. And the values of this will be 9 and 2. Okay.
Yes.
It is recorded or not?
Yes, sir.
Okay. The talk is recorded or not?
Yeah, it is recording, sir.
Good.
Okay. Sir.
Then this matrix 3i, 2 plus I tell you, whoever is really interested in quantum computing, you have to do all these groundworks. Then things will be very easy for you. In fact, my guide or my professor say, you be strong in mathematics, life will be easy. Okay, life will be easy actually. This is a skew Hermitian matrix. This is Hermitian. This is skew Hermitian. See, 2 plus I minus 2 plus I. Yes, Hermitian. And that means this is the real part is negative here. And if you take the characteristic equation, you are getting lambda square minus 2i lambda plus 8 is equal to 0. And if you solve this equation, you will get 4i and minus 2i as the eigenvalues. That means the eigenvalues of a Hermitian matrix are real. And the eigenvalues of a skew Hermitian matrix is totally imaginary or even 0. They may be 0. Okay. So these are imaginary eigenvalues and these are real values. For a unitary matrix, what happens? Let us see, which is complex and which is also whose rows and columns are orthogonal or orthonormal. Okay. Look at this. So let us take some matrix C. This is 1 by 2i, 1 by 2 root 3, then 1 by 2 root 3 and half I. Okay. This is unitary and its eigenvalues are half root 3 plus half I and minus half root 3 plus half I. These are the eigenvalues. They are complex. Okay. So, these are the conditions. Then we go to eigenvalues and eigenvectors. These are all required. That is why I am refreshing just. Maybe those who are teachers or researchers, they may go through any standard book, or I'll give you the references also. Okay. So that you practice all these things. Now, what are eigenvalues and eigenvectors? Whenever we are applying a matrix A on a vector X, it goes to something, some say scalar lambda X. Okay. So what happens? This lambda, it may be a vector also, I mean column vector. So this lambda and this A have got a relationship, very close relationship. In fact, they are the characteristic roots. They are the characteristic roots of this equation. All right, characteristic equation. From the characteristic equation, A minus lambda I is the matrix X is equal to 0. And remember, X will never be equal to 0. So after putting this, we get the lambda values. And they actually, what do they do? A matrix actually transforms. A matrix transforms data, right? So transform means, as I said, changes position, shape, changes the position, shape and direction of some input. Okay, of some input. That means input the matrix A and this is the output. So A takes care of all these, position and shape and direction. Position and shape are taken care of by lambda, direction is taken care of by eigenvectors. Okay. Direction is taken care of by eigenvectors. For example, I will give a simple example. All of us, we use rubber, I mean, in packing things, a small circular thing, rubber band, okay, a rubber band, like this, okay, typical rubber band, and we stretch it, like this. That means if it is a circle, you'll see that if you stretch it, it looks like an ellipse. So here a symmetric matrix is involved in this transformation. Okay, a symmetric matrix is say 6, 3, 3, 5, like this, or 3, 6 even, 6, 3, 3, 6. Okay, like this it is here. And the lambdas you get, lambda 1, lambda 2, they will take care of the magnitude, I mean this particular shape, how it will look like. And the directions, it was 1, 0, 0, 1, sorry, 0, 1, 1, 0. Now it is 1, minus 1 and 1, 1. We change like this, 45 degrees, rotation, okay. And stretching is also there. So matrix actually transforms the entire input into some output in a different, takes to a different region, all right. And In the new space, the eigenvectors, as I showed, 1, 1, 1 minus 1, they are the eigenvectors. Okay. So look at this. In our terms, we write AV is the vector is equal to lambda V. Take this example. Lambda is a scalar, V is a vector, A is the matrix 2, 0, 1, 2. This is a matrix. And it is operating on a point or a vector 0, 3. We get, look at this, 2 into 0, 0 into 3. We get 0. 1 into 0, 2 into 3, we get 6. That means 0, 3, this vector has been transformed to 0, 6. And we see that this is 2 into 0, 3. That means this is our vector. This is A. This is the resultant. Now again, this is 2B. So lambda B, AB is equal to lambda B. So our eigenvalue is 2 here. And 0, 3, the direction, same direction, is the eigenvector. So 2 is the eigenvalue. That means the vector has been elongated twice, or doubled its length in the same direction, because 0, 3 is the eigenvector. This is a simple visualization of how the matrix transforms the vector 0, 3. Okay. Okay. Now, in classical computer science or computation, whatever input you have, suppose I am writing A, B, C, D, E, 1, 2, 3, 4 as my password. Okay. The computer understands only 0, 1, 1, 0 like this. All these will be in bits, zeros and ones. Even when we type something also, the computer takes everything as this, zeros and ones, binary digits, 0, 1. Suppose I write 7998, it will be decoded in 0, 1, binary representation. Then classical computers accept this, and only 0 and 1, combination of concatenation of zeros and ones. However, what happens in quantum computing? In quantum computing, we take same zeros and ones, but in a different manner. Same zeros and ones are taken in a different manner. How they are taken? They are called qubits. They are called qubits. The B is making this. Okay, and this will be the main study in this presentation, qubits. Okay, we call them quantum bits. Qubits means short form of quantum bits. Okay. All right. So while dealing with qubits, we should understand in detail what is a qubit, what operations we can make on qubits, and how do they behave, or how do they help us in computing actually. Okay, so a qubit can be 0 and 1 simultaneously. A qubit can be 0 and 1. What happened? What happened? Problem or what? Is it visible now? Hello? Hello? Am I audible? Hello? Shilpa madam?
Yes, sir, audible.
Ah, now it came. Right? What has happened? All right. A qubit can be 0 and 1 at the same time. We will be calling it superposition. All right. Same time or simultaneous. Okay. Simultaneously. So how can we imagine it? We know that quantum computing has come from quantum mechanics. The origin is actually from quantum mechanics, from physics. In quantum mechanics, we talk about particles and waves. Okay. And they actually gave the idea of qubits. Right. So if somebody really interested, he can have a very refresher course on quantum mechanics also. I'll give you references. So physically, I'm writing it. Physically, a qubit can be made from, I mentioned physically, a qubit can be made from quantum particle that has two distinct states, maybe horizontal, polarized, or in fact and vertically polarized. Okay. So similarly, we can have this. Photon particle can be polarized both vertically and horizontally. Okay. Double slit experiment in physics makes this. Okay. It's called double slit experiment. In fact, it goes like this. There is a source of particles like this, but the first there is a single hole, sorry, double hole. So particles will move here and they will collide here in the wall. From there, they found that it is of wave and particle at the same time. Why it is going? I'm not getting it. Why the screen is vanishing? Can anybody help, please? Sometimes the screen is going away. I'm not getting it. Yes, I do agree. Screen is not visible. Something happened. Can somebody guide me?
Sir, excuse me.
This whiteboard vanished.
Whiteboard. Whiteboard is not. Whiteboard is not visible.
No, whiteboard is not on my screen.
This one, main application. Just minimize this application, sir. You will get that whiteboard.
No, this is not whiteboard. This is my A is coming. I mean, paint is coming. Because
Paint is coming.
So, because paint, the letters are not clear on paint.
No,
Yes,
sir.
yes, yes, sir.
I mean, whatever you have used till now, it was visible, whatever you are writing. Now again, you are went to only video mode. I mean, you are only visible, not the board.
Once again, you share that screen, sir.
After sharing the screen, you use the whiteboard in the WebEx, sir.
Whiteboard, yes.
Okay. Share. Okay. Now here, how can I, you are sharing screen, how can I get the WebEx whiteboard?
No, you go to the meeting app, sir, where you have joined.
Minimize this, minimize, sir. Minimize it. This. Minimize this window.
Oh, this window I will minimize.
Yeah, minimize this window.
This one.
The app is open
Ah.
now, sir.
Now it is coming sharing.
No, sir. First time, how you
Sharing content. Yeah, we are getting message sharing content. But
no stopped
we
sharing.
didn't get it. Just now we got that message.
No, sir. First, I told you to use the WebEx whiteboard, na, sir. At that time, have you switch it to whiteboard? Same way you try, sir. Once.
Now, is it shared?
No, sir. You click on the whiteboard. Have you clicked on the whiteboard?
Yes, yes.
3 dots are there now, sir. 3 dots are there now.
Yes, that one.
I think it is visible. Visible? Resume. Resume. Correct? What is happening?
Sir, open this
Now is
WebEx.
it visible?
No, sir. It is coming. Stopped sharing.
Stopped sharing. Yeah.
There is some problem. Okay.
Madam asked sir to go to the 3 dots.
Yes, I am going to
Then
the 3
find
dots.
the
Then I
whiteboard.
whiteboard.
Yeah, whiteboard is there, sir.
Yeah, select that one, sir.
Selected. Open for
Yes.
all. It is saying.
Yes, sir.
Open for all. Continue.
Continue.
Writing opening a whiteboard.
It is opening for you, sir.
Uh-huh.
But we are not able to see the whiteboard.
Stop. Resume. Resume. When I type.
Stop sharing content.
Is it visible now?
No, sir.
No, sir.
Once you stop sharing and go to only whiteboard, sir.
When I'm sharing, it is hiding. I don't know why.
Initially stop the sharing, sir. Initially stop the sharing and you go through 3 dots, find out whiteboard.
Whiteboard is opening for me.
Yeah.
But it's taking time. Taking time. It's saying you opening a whiteboard.
Sir, can you please leave and join again so that maybe problem, any network problem is there, it will be solved.
I think.
Otherwise, madam, ask sir to continue with paint also. No problem.
Okay, sir. I will. Now directly you open whiteboard, sir. Once try.
Unmute, sir. Sir, unmute yourself. Yeah.
You are not audible, sir. It's not audible, sir.
Hello.
Yes, sir.
Yes,
Now
sir.
it is.
Audible, sir.
Now I'll go to whiteboard. Whiteboard is not opening.
Sir, first, sometime you switch off the video. Maybe your network is very low. So for video, it will take more. Are you able to open the whiteboard, sir? Sir, now you can try to open the whiteboard, sir. I have made you the co-host. Sir, sir, are you available? Sir? It is not audible.
Now am I audible?
Yes, sir.
Yes, sir.
Am I audible now? Yes.
Yes, sir.
Yes, sir.
Why this? Uh,
You try with paint only, sir. Then.
I'll try with paint only.
Yes.
Sir, voice is not audible.
I think now it is audible. Hello.
Yes, sir.
Yes, sir.
Now it's audible.
Yes, sir, okay.
Now screen is visible.
Yes, sir.
Okay. Okay.
Yes, sir.
Okay. Okay, whatever. Why it is coming like this? Process saves pen. So now we shall go to what is our bracket notation. Now it is coming. Is it okay? Is it?
Yes, sir.
Am I audible?
Yes, sir.
Yes.
Yeah, sir.
Bracket notation or Dirac notation. In fact, Dirac is Paul Dirac, the veteran German scientist who gave this. In fact, he first introduced quantum computation, actually, quantum mechanics. Okay. So here we shall see how a qubit is actually represented, right? Let us go to that. Right. Okay. How do we represent a qubit? We represent qubits as zeros and ones. We represent qubits as zeros and ones as follows. See, there is a bracket here. We call it ket notation, ket. And this is actually this vector 1, 0. Okay. That is why I'm talking about column vectors. This 0 is 1, 0. But I will explain why it is 1, 0. And 1 in ket notation. This is ket. Bra notation is like this. If I write psi here, this is bra and this is ket notation. So both are called bracket notation. Is equal to 0, 1. That means when we put like this as input, the computer will understand actually 1, 0 vector. If we are 0, this is called a state. This is called a state, quantum state. Quantum state. And this quantum state, 0 means 0 is 100%, means with maximum probability of 1, 0 is there. And 1 is available here with maximum probability in the second position. And I'll tell you where actually we are. When we are representing like this a qubit, where we are. They are in complex numbers, we are in the complex plane. They are in the complex numbers, we were in the complex plane. But here actually we are on a sphere, like Earth, so to say. Okay. And we call that block sphere. I'll just give you the idea, and block sphere computations will be after a little time, after understanding qubits in detail. See here. Suppose this is the equator. This is the equator. Okay, this is the plane. That means if we slice that sphere, it will look like this. This is the upper half. This is the lower half. And this is the North Pole. And we name it as 1. And we name it as, sorry, ulta, reverse. The 0 state is on the top, right? 0 state is in the top. Say x-axis, this is the y-axis, and this is the z-axis. So on top of this is the North Pole, we have your this one 0, and in the south pole we have got 1, this state. All right. Now you can imagine why I was talking about e to the power minus I pi by 2 or e to the power I pi by 4, all this, because we will be moving around this, and this is a unit sphere. And we call this a Bloch sphere, B-L-O-C-H. And this was given by Felix Bloch. He is a veteran, quantum scientist, quantum physicist, right? We'll be coming to that later. Let me go to the initial calculations and presentations of a qubit. Okay. So whenever we are moving like this, or see, suppose this is a state, quantum state, 0 state, 1 state. Suppose we want to come to 1 state, we have to apply a gate. We want to take this to, say this is minus y axis. So this is, we call it I, this is minus I, this as plus, this as minus, or x axis, minus. Okay. So all these states, how to attain these states, okay, in through matrices or gates. Okay. And this will be done by only complex numbers, states will be in complex numbers, transformations will be through matrices. That is why complex numbers and matrices matter. Okay. Okay. Now, so as I said, again I am writing 0 state is 1 0, and 1 state is 1 is equal to 0 1. That means this state will be in the south pole, this will be in the north pole, top, and this notation, something, some input here, dot means input, is called Dirac notation. Okay. Now, what is the difference? See here, classical computers use only 0 1 strings, 0 1 1 0 like that, strings. Okay. However, here we are using vectors and 1 and 0 simultaneously. So we call it superposition, superpositioning. That means our information which we put as an input may be oscillating between 1 and 0, like a photon particle. Okay. Oscillating between 1 and 0. Sometimes it is 1, sometimes it is 0, or some percentage in 1, some percentage in 0. So this 0 is at 1, this 1 is at this one. But if I take a combination of 0 and 1, these two, they will be somewhere in between. That means somewhere inside the sphere or on the boundary of the sphere. Bloch sphere. Okay. In quantum mechanics, a quantum particle may be in 2 states simultaneously. Okay. A qubit in superposition is also maybe at 0, maybe at 1. So, what is superposition? A qubit may be at 0 and 1 simultaneously or at the same time. This seems a bit absurd, but we will see how actually this is happening simultaneously, same time. So we don't say that it is a single position. That is why we call it a superposition. Then how to mathematically model the superposition? How to mathematically model the superposition? How to express it? We express it like this. Let a qubit be represented by a column vector. Sorry, column vector like this. So qubit means we name it as psi. This gate notation, KET gate notation, and we call it alpha beta. I am not taking 0 1 or 1 0. Alpha beta, any qubit. Okay. So what is alpha and what is beta. Alpha is represents the probability. Probability will be later, coming later. Alpha represents the qubit at zeroth position, at zero state, and beta represents the qubit. Qubit means this psi, this qubit at one state. Okay, one state. Now that means this psi is at both 0 and 1 simultaneously in a superposition. Okay, that means this qubit psi is in superposition both at 0 and 1, and alpha and beta are some values. We'll talk about it. They quantify how much they are, how much psi is it at 0, how much is at 1. Okay, so now how to measure a qubit? Next question is how to measure a qubit. This word measure is very important. See, once you measure a qubit, it goes either to 0 or to 1. Once we measure a qubit, it collapses to, the very word is, it collapses to either 0 state or 1 state. Okay, so it is in the same principle that when a photon particle is either horizontally polarized or vertically polarized, if you want the vertical position of that, it collapses to vertical position. If you want the horizontal position, it collapses to the horizontal position. So mark it. I am taking an example of a qubit. Let psi 1, this a qubit, be equal to this vector √3/2 and 1/2. That means my alpha is √3/2 and beta is equal to 1/2. Now you marked something already. Alpha square is equal to √3/2 square is equal to 3/4. And beta square is equal to half square, that is equal to 1/4. Now alpha square plus beta square is equal to 3/4 plus 1/4 is equal to 1. This is the most important condition for any vector to be a qubit, any column vector. Okay, this is the most important. That means alpha squares and beta square sum should be 1, then only it will be a qubit. Okay, what does it mean? That the probability of this psi 1, this qubit, to be in the position of 0 is 3/4, and the probability of psi 1 to be in the position 1 is 1/4. That means it lies 75% at 0th position and 1%, 25% at the 0th position. So I'm writing it, that will be better. Okay, this means that this psi 1 lies at 0th position 75% and one state 25%. So at psi 1 is 75% at the state 0 and psi 1 is 25% at 1. state. So this is superposition because it assumes positions at two places at the same time. Percentage differs, but it is present like that only. That is why this is a qubit. Okay. So you can mark it root 3 by 2 plus 1 by 2. Suppose I write it I root 3i plus half j in a xy plane. So this represents a unit vector. Its magnitude is 1. Its magnitude is 1. So unit vector. That means this can act as a orthonormal vector, okay, to some other vector. That is why that orthonormality was important. Orthogonality in unitary is important, like that. Okay. Now let us see if this is a qubit. Consider psi 2 is equal to 2 by 3 and then root 2 by 2. Root 2 by 2. So alpha here is 2 by 3 and beta here is root 2 by 2. So alpha square plus beta square is equal to 2 by 3 mod square plus root 2 by 3 root 2 by 2 mod square, and it is not equal to 1. Okay, so this is not a qubit. Psi 2 is not a qubit. Condition is violated. Okay, so how we write it? So once we write psi as alpha beta, now the matrix comes into picture. That is, this is alpha 0 plus 0 beta, isn't it? Because this is 2 by 1, 2 by 1, 2 by 1, 2 rows, 1 column. So we can add it. And this is alpha into 1, 0 plus beta into 0, 1, a linear combination of the vectors. Now, this is, what is this? 0 state. This is 1 state. Okay. So this is Dirac notation or Ket notation. Dirac notation. Okay. They are called Kets. Now let us go to, so we have got an idea about qubits now. Another thing you might have seen, those who have gone through the literature, there are not only single qubits like this, there are 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, like this. They are there. Or maybe sometimes like this. Okay. So what do they mean actually? 2 qubits, 3 qubits, and as we say, quantum computers nowadays, they're IBM and what is the other? Google. IBM and Google, they talk about these bits, million bits. Okay. The more bits are there, you can store more data into it in matrix form actually. All are matrices here. Okay. So that is why computation becomes easy theoretically. Real-time application is yet to be done. Theoretically, many things have been achieved in quantum computing already. So let us talk about block sphericity. Block sphere. Okay. So let me draw it again so that we'll have some rotations and positions. I'll give you some YouTube video links you can see so that will be easy. Okay, this is Z. That means this is our 0 and this is 1. And if I take this as x-axis, then I'll write this as plus, this as minus, and y, this is I, this is rotate minus I, like this positions. Okay. So what happens? Minus I, plus I, minus I. So let us talk about this. Psi is equal to 1 by root 2, 1 by root 2. Okay. And this is actually 1 by root 2, 0 plus 1 by root 2, 1 in ket notation. Okay. So the probabilities are half, half, half and half. Alpha square is equal to half, beta square is equal to half. That means this is this, sorry, ket notation. This qubit psi is 50% in the zeroth state and 50% in the one state. Means it is in between here in the z axis, in between, oscillating between 0 and 1, this axis, z axis. Okay, it is oscillating in between 0 and 1. Okay, so this is the truth, that superposition. If I say that I have collapsed it into 0, then it will go to half into 1 0. Sorry, 1 by root 2 into 1 0. That means it has collapsed. That it becomes simply 1 by root 2, our usual data in the classical computer. But this is quantum data with probabilities. This is quantum data. Okay, superpositioning is already there. Okay, so the video link I will give, you see in YouTube the three-dimensional figures and the animations are well there, so you can follow the positions of different qubits. Now, manipulating, I will request all to manage manipulating time. Actually, I will take a little more time. Manipulating a qubit through gates X, Y, and Z gates. All right. In classical computer, we use logic gates. We use logic gates. But here we go use quantum gates. Okay. We use different gates called quantum gates. All right, to process the data. So how we do it? How we do it? I'll give you one, two examples like this. Suppose, what is X gate? Now suppose I use X gate and I operate it on the zeroth state, X gate. It will take me to position 1. Why? See here, in the block sphere, we have got 3 dimensions like this. This is Z axis, this is X axis, sorry, this is X axis, this is Y axis, and this is Y axis. So this is like this. If this is plus, this is minus, this is plus I, this is minus I, and this is 0, this is 1 in the block sphere. Okay. So what happens? X, this X actually moves like this, upward, downward, 180 degree, pi radians, or this way, 180. This is 0 state, this is 1 state. So when you operate X gate on 0, you straight come 180 degrees to 180 degrees, pi radians. Okay. If you apply the X gate on 0, you are coming to, this is defined like this, X gate. So X gate flips the qubit by pi radians. X gate flips the qubit by pi radians. All right. Since it is at the boundary and on the sphere 0, but as I said, it may not be 0 and 1 only, it may be somewhere like 2 e to the power I pi something, okay, pi by 2 or pi by 4, somewhere in the angle in between, because this is the sphere, okay. On the surface of the sphere, somewhere the data is being taken and we want to transform it to different places. This is a unit sphere, okay. So similarly, what does the y-gate does? I'll give you examples so that how it is transformed, you'll see through matrix form actually, okay. Now y-gate. Y-gate also transforms, say it was plus I, it was minus I, it is also moving 180 degrees, pi radians, right, pi radians. So y-gate also transforms the qubit in pi radians, okay. And z-gate, what happens here is with z-gate, around z-axis you move, around z-axis you move. Z-axis is here. This is z-axis. Okay. So we can move like this. So we have got two pi radians. But actually when we operate, either you are moving this way, or this way and then this way. So we put it as again pi radians. Okay. So in the block sphere, to manipulate the qubits, we take the help of our X, Y and Z gates. So how do they look like actually? You see, X is, I have already operated it. X is actually this matrix 0, 1, 1, 0. Therefore it flips. And Y is 0, minus I, 0. So complex numbers. This is a complex matrix. And Z is 1, 0, 0, minus 1. So second argument becomes minus the beta part here. Okay. So let us operate one by one on some qubit and see what is exactly happening here. Okay. Look at this. Suppose my qubit is psi. Let psi be equal to alpha beta. And I am applying X gate. X on psi is equal to 0, 1, 0, 1, 1, 0 with alpha beta. We will get, if you multiply, see here, first it will be 0 plus beta, then second will be alpha plus 0. So beta will come here, alpha will go there. So flipped, psi is flipped. That is why when you operate on 0, x on 0, it goes to 1. 180 degree it is flipped. Okay, you can verify it. See, X gate is 0, 1, 1, 0. And what is your 0 state? 1, 0 is equal to 0 into 1, 1 into 0. So it is 0. 1 into 1, 0 into 0 is 1. So this is your 1 state. This is your 0th state. And this is 1 state. So 180 degree rotation is there. So that is why X gate is transforming this to from 0 to 1 state. Now what about Y? Y is 0 minus I 0. Now let us operate on this. Let me take this as psi. Let see, all these are superpositioned qubits. root 3 by 2, 0, 0 state, and half at 1 state. And I am operating y on this. So y of psi will be equal to y of, sorry, these calculations are very important. Y of psi is equal to y of root 3 by 2, 0 plus half 1 state. That is equal to root 3 by 2. These are linear operations. So this can be out y of 0 plus half of y of 1. And that is equal to, see here, after calculation you will see root 3 by 2, it will be I1. In fact, we can multiply here itself. Okay. So I into 1 state minus half into 0 state. Half I into 0 state. This will come like this. So there is another flip here through 180 degree and positions are changed. Okay. This was plus here. Now this has become minus. Root 3 by 2, 0 was there. It has gone to 1 and this has gone to 0 with coefficient I. That means in the around the y-axis this has rotated. Okay. Around the y-axis this has been displaced, okay, through 180 degrees. Unitary matrix. Yes. Unit. Okay. Now Z gate same thing. We'll take an example. Immediately we'll compute. Now Z of say alpha into 0 state plus beta into 1 state is equal to alpha Z of 0 plus beta Z of 1. So the scalars come out and this operates on 0. What is 0? This is 1 0. This is 0 1. And what matrix is there? We have 1 0 1 0 0 minus 1. Okay. So this matrix operates and ultimately we get alpha 0 minus beta 1. Okay. After the multiplication. Why I am saying this, I have taken a 2 by 2 matrix here of zeros and ones. Now you see, you take a very large matrix. Very large means many ones and many zeros. However, satisfying the condition that all the coefficients square, when you add them, there will be 1 for each column vector. Then there will be larger qubits. Okay, there will be larger qubits. That means any matrix multiplication operation, all these can be done through simple these numbers. Okay, that means we are compressing a matrix into single digits like qubits. If it is a 2 qubit, you can get a 2 by 2 matrix. 3 qubit is 3 by 3. And we'll go to tensor multiplication also. Tensor product, you'll see how 3-dimensionally we can, that is why your images or objects can be manipulated. And they are talking about transportation, teletransportation. All right. So I'll talk about little about global phase and local relative phase. Global phase and relative phase. Suppose we have already done Pyridines. Okay. So consider this 1 by root 2, this qubit in superposition plus 1 by root 2 1. And apply Z gate. What happens? It goes to 1 by root 2 0 minus 1 by root 2 1. Okay. Minus 1 by root 2 1. Now the qubit has rotated by pi radians. The qubit has rotated by pi radians.